So, what's the story with ketones? Why have we turned our back against them? Because we've not really done any kind of examples with ketones at all, have we? When it concerns rings, when it concerns drawing the majority of these structures, we have focused on aldoses and we've kind of turned our back against ketoses, but I want you to be aware that ketoses do things that are very similar to aldoses. They might look a little funny in the beginning, but it's there. They will do it. Be comfortable with them. There shouldn't be a problem as long as you follow the rules. And that's the kicker. You've got to be able to follow the rules. So I want to take a look at one of these ketoses that we should become familiar with, and that's the ketose for fructose. So I want to start off by drawing the structure for fructose, and of course that's CH2OH at the top, and then down here at the bottom is CH2OH. At the second carbon is where we see the ketone, and then for fructose we'll see another 3 carbons, and we'll do OH to the left, OH to the right, and OH to the right, of course, because we're concerning ourselves with D-fructose. And just like before with ketoses and aldoses, the story's no different. We have a carbonyl group here at the top. It's just in the form of a ketone functional group instead of an aldehyde functional group. And we've got some OH groups in the actual structure itself. So we're still going to see an intramolecular reaction happen, and we're still going to see these rings form. They might look a little different in the beginning, but the story with the ketoses is that typically when they do make these rings, you will get choices from the rings. So I'm going to put that in big words up here. Ketones equals choices when it concerns ring structures. So that's the problem with the ketoses and the aldoses. Alright, so ketoses also exist predominantly in the cyclic form. They're just like aldoses. That means if I compare the straight chain with the ring structures, well, when I look at those two structures, the ring structures are going to be more dominant. They're going to be in a higher percentage. I'm going to see most of these ketoses in ring structures just like the aldoses. Again, the story's no different. They should be the same. It's the same type of functional groups, right? So depending on the number of carbons, that might make my ring look a little different, but it's traditionally the same thing. So let's look at this a little more closely. We see this sugar, and we already said the C double bond O is exactly the same as the aldose, and these OH groups are on the molecule just like the aldose, so we should see a ring structure that forms, right? Okay, so we know that the carbon involved in the carbonyl right here is going to be hooked up to one of these other carbons to make this ring structure. The question is, well, which one will it do, and how does this ring look a little different? Okay, well, we said that we've got some choices here. So when this molecule makes a ring, it's going to react with one of these OH groups. Typically it's the OH group that's further away from it, so it can make the bigger ring. And we still have this CH2OH group that is basically out there. So far, that's basically out there that hasn't been touched. So this is one option for it. So we see a ring structure just like before, an oxygen bonded up to the carbon of the carbonyl. Alright, so this oxygen here is this one. And we've got a carbon that was involved in a double bond O, but now it is not. This has an OH group on it. But you got to be careful, because unlike the aldoses, this carbon also has another carbon on it, and it's a CH2OH group. So this carbon also has a CH2OH group on it, where the aldoses did not have that. That's because the aldehyde was at the end of the chain, not in the middle of the chain. So we can't forget about that extra CH2OH. Alright, so here we see the next in line is this green carbon, so I'll do it here. And then the next one is this purple carbon, so I'll do it here. And then the next one could be maybe this brown carbon, and that had this blue OH on it. So let me just do that one blue as well, right? So here's this blue carbon that basically had the O on it. So there is the formation of the ring. It's a 5-membered ring. So this is a furanose that it makes, right? So fructose is going to end up making a furanose ring, and then off of this blue carbon, that is where we see the other CH2OH group. So up here is the CH2, and there's the OH that's involved. Okay, so I just want to clean this up a little bit, right? So I'm just going to draw everything in the same color now. We know that this is a 5-membered ring, and 5-membered rings look like that. We also know that this carbon has a CH2OH group, so I can draw it that way. And I know that this also has a CH2OH group, so I'll draw it that way. And this OH group could point down, or just like the story was told videos and videos back, it doesn't change. We could see an OH group that points up, and the CH2OH that points down. Okay, so we still see an anomeric carbon. That OH group does have a choice. It can be pointed down, or it can be pointed up. I mean, that's up to you, however you want to draw it, or whatever the question says to draw it that way. Notice also at the same time, this carbon is the OH group. That's the anomeric carbon. This green carbon, that's a chiral carbon, right? We see the OH that points to the left. So therefore, in this structure, the OH is going to be pointed up. So we need to draw OH pointed up. This purple carbon, we see the OH on the right-hand side, so we'll put the OH that points down here. So there's the right-hand side OH. And then finally the blue one, well, that OH we don't have to draw because that was the one that was involved in the oxygen hookup. So this was the oxygen in that OH group, but it's just not an OH group now. It's involved in the ring, so that's what created the glue that held this ring together. So there's the structure for two different cyclic fructoses. So this thing is going to be called D-fructose. And this one is also D-fructose because that's where we started, right? We didn't change this group. I mean, that kind of stayed the same. So we can call that fructose because it came from D-fructose. Now, the question is, well, what about alphas and what about betas? Okay, so the OH here is pointed down. So this is called alpha. And the OH here is pointed up. And this is called beta. So this was just like before, right? We said if the OH group points down in the 6-membered rings, that was called alpha. If it points up, that was called beta. So the same exact thing is happening here. All right? Okay, so there's alpha and there's the beta fructose. Now, we're calling it fructose, but really this name is going to change slightly on you. It's not something that we really preoccupy ourselves with, but this is not really fructose anymore, but it's a fructofuranose, because it's in a furan ring, right? So that's really the proper name that we give this sugar, but I'm not really going to be focused on the proper names like that. Again, it's just drawing these structures, understanding these structures, understanding why we're doing what we're doing. That's really the take-home message. Okay, now the other story is there's another possibility for the ketoses. And here we took this aldehyde, or this ketone group, and we reacted it with the number 5 carbon. But in actuality, we can also take that ketone group and react it with that OH group as well to make a six-membered ring. And we've already said six-member rings can exist, so why shouldn't they happen here? And they do. So the other two options that I can get with the fructose is a six-membered ring, and I'm just going to quickly draw those. Hopefully you can replicate it when you try it yourself, but we see this six-membered ring here. On this first carbon, or on that second carbon, that carbon has a double bond O. That gets converted to an OH group. So that OH group can point down or that OH group can point up. Not only that, but this carbon that had the ketone group also had a CH2OH group on it as well. So that's kind of what I have to show here, CH2OH group. The second carbon was green, right? So I can use the green color here and there's no difference there. That was on the left-hand side of the fissure, so therefore this points up. The next carbon in line was the purple one. So when I take a look at it, the OH group was on the right, so therefore this goes down, so the OH group points downward. And then the problem is that it didn't hook up with this blue carbon, right? The hookup happened between here and the last OH group to expand the ring a little bit. So this time we do have a carbon in the ring. This blue carbon has the OH to the right, and therefore here this goes down. So we do see another OH group that happens there on carbon number 4. Now, if I look at the differences in the structures, notice that in the 5-membered ring, I had a CH2OH group that was hanging off. Well, this is the CH2OH group right here. It was that OH group that bonded up to make the glue on this ring. So that's why there's not one of these hanging off of these structures. All right, so the same thing is going to happen here. This is D-fructose, and this is D-fructose. If I look at the OH groups here, in the first one my OH group is pointed down, so this is alpha, and here the OH group is pointed up, so this is beta. So there's the alpha version and there's the beta version of the fructose. If I really want to properly name it, I wouldn't use fructose again. I would use fructopyranose, because this is a six-membered ring now that my fructose has made. So alpha D fructopyranose, or beta D fructopyranose. It lets me know what sugar was making the pyranose or the furanose rings, and that's why we incorporate them into the names. All right, so we'll keep trucking on. I know that you enjoy these structures. I know that you love listening to these boring lectures. I know that you love listening to me ramble and ramble and ramble on for minutes at a time, but we're almost finished, I promise. So just keep trucking on. You're almost at the finish line. You're almost there.